Here we want to demonstrate three fundamental concepts. First, we show that PCA and linear autoencoders are equivalent. And then we add the deep learning steroid to the linear autoencoder and make a nonlinear version and see the improved performance. So let's start with the common way that we compute the principal components. Here I assume that you remember this, but as you know, PCA finds the direction of maximum variance and project the data over these directions that are eigenvectors of the covariance matrix. We use the top k eigenvectors, and there are ways to choose k based on the amount of variance that the chosen components will explain. We discussed that PCA basically finds this projection W that has a rank of Ka and minimize this reconstruction error. Okay, so here is our PCA class. Basically centers the data to 0 and then compute the singular value decomposition. If you don't remember SVD, please go ahead and review this. And then we extract the top k components or the eigenvectors. So SVD basically rank all of these vectors based on the top eigenvalues. It is already sorted, so it's enough to just choose the top k. Here I'm calculating the explained variance. Then later we want to compare it to the linear autoencoder. And this is how we find the z, or the latent space. It's basically the projected x over these components. And now it is in k dimension. We can decode it back using the transpose of the matrix that we found in the encoder. And as we discussed, basically these are orthogonal vectors that correspond to a rotation. And the inverse of a rotation matrix is basically the transpose of it. And finally, we compute the reconstruction error, which is the loss that we minimize. Okay, so with that, let's write the linear autoencoder. Basically, instead of using SVD, we'll use the gradient descent to find those subspaces. So I have a class, the linear autoencoder, and remember here we find the first set of weights that encodes the data to Z, and the decoder is basically just a transpose of it. So we don't want to learn it twice. It's basically tied together. So let's call it a linear autoencoder with tied weights. Okay, so we want to show that this linear autoencoder with a MSE loss and these tied weights, once converged, it will span the same subspace as PCA. This is actually theoretically shown in this paper, if you're interested, by Baldi and Hornig back in 1989. But here we are doing it empirically to just show the results are the same. So the goal is to show that the span or the space of the Z is the same. So note that when I'm saying span, means that latent space can rotate. It is still the same space, okay? So the weight can differ by rotation, but the span stays the same, okay? So let's define the init method. So let's define a weight matrix that basically works for both encoder and decoder. Here we are starting with a randomly initiated weight. Ideally, we want this to be small, but let's just start with this. And then this the input dimension and the output dimension. Well, the output is the same, just latent dimension. Okay, so that's the initial parameters and dimensions. Let's write the encode method. Okay, so that's what we have. Encode is basically a linear projection of x by w, and then we have the decode. which is basically the transpose, or bring it back to the same angle. Then we have the forward, which is the encode, and the decode that gives us the reconstruction. Let's also return Z. So in case we want to compare the projection matrices that eventually defines the subspace spanned by the autoencoder, let's write this. Okay, so we need to do this with torsionograd. Maybe we can add the decoder too. This way we can use this function for the reconstruction. Okay, I think we should be good for now. So now what I want to do is to empirically show that PCA and this linear AE or autoencoder learn the same subspace. So what we will do, we will first create a dummy data set on a 2D linear space so maybe we can frame it this way. We can create a data set that lives on a two-dimensional linear manifold, but this two-dimensional manifold lives in a 50-dimensional space. So both PCA and linear AE should find this two-dimensional manifold. And then we will compare the learned subspaces between them. Okay, so let's generate this synthetic data. Like I said, on 2D manifold, but in a 50-dimensional space. Okay, so the true dimension will be 2, and the dimension that they live in, or the ambient dimension, will be 50. And let's define a number of samples, let's say 1,000. And then we will generate the data. So basically what I want to do is to generate X from a Z that we know, the Z lives in this 2-dimension, and then project this to this 50 dimension. Then let's add some noise too. So that's what we will do. So for that, I need to define this true W that we want to find. Let's see the suggestion. I mean, we can go with this, but I like to have this at the beginning. Then we have Z. So Z will, here, yep, so Z lives in this true dimension, right? Which is 2 here. Okay, so then X will be this and ambient dimension. It should work. Let's reduce this to make it easy for them to find. So that's the data. Let's see. Okay, now we can find the reconstruction error with PCA, and then we will compare it to the linear autoencoder performance. Okay, for PCA, it's enough to just call the class that we wrote. We need to define the components, of course, which here is it's the true dimension. Now it gets it. Okay, so then we do the fit, which is basically the SVD and picking the first 2 component. Then we can compute the PCA error. Right. Let's run this. Okay, so, and then let's do the linear autoencoder. So we have a linear autoencoder, and okay, then we need an optimizer, of course, to handle this. Let's just use Adam. What else? Oh, we need to center the data. So let's just use the mean and remove this mean. Okay, and now we don't need to really normalize the variance. Let's just use this because we want to compare the variances, and we didn't do it in PCA. So let's not call it centered. Normal then. So we are going to call it centered. Okay, so now we have to train. So the training loop will be, first we need to initialize the losses, then for epoch or old training loop. Then we append the loss. We can do a print, and I want to plot or print out the final loss too. Okay, so let's run this. Okay, something is wrong here. I think, yeah, the initialization that I discussed here, this is too large. We have to reduce this. Okay, so let's try again. Yes, it works now. What's next? So we can also compare the subspaces if they are the same. To do that, we need to look at the projection matrices and then look at the distance between these two matrices. So a good distance here will be Frobenius norm, and I'm going to use that. So if you're not familiar with it, you have to check it out. So to get the projection matrices, we have to use the basis vectors that we found in PCA, which was the components of the PCA, and for the linear autoencoder, it was the weight matrix. So here for PCA, for example, we have the projection matrix, this. So note that I'm not going to compare the bases in the latent in PCA and linear autoencoder. The reason is they are not unique and they can rotate. But here when we look at the projection matrix, we don't have that problem and we can directly compare them. Okay, so with that, this is the PCA, and for the AE, we already wrote the method, so just gonna call it. And the distance or the subspace difference will be the norm of the difference. How large is the difference, right? And here note that, yes, we are getting the item and we can print this out. Okay, let's compare this. Oh, I forgot to transpose. And note that difference is zero. So they are practically the same. Okay, great. So this is checked, and we showed that linear autoencoder naturally discovers the PCA through this gradient descent and the training, which is pretty important in the sense that the optimization finds the right representation in an automatic way or an end-to-end way. We didn't really use any math. We didn't use SVD or anything like that. Okay, so with that, let us do the nonlinear autoencoder, and then we can compare the representation of the nonlinear autoencoder with the linear autoencoder. And I want to show that this representation is much richer and we can find or represent much complicated manifolds. So to do that, I'm going to use the dataset, Swiss roll dataset from Scalar. So if you haven't seen this, it's basically a dataset that looks like this. It's a Swiss roll, and it's difficult to find this with linear planes because of the shape. And also we have points that may be close to each other, but they are living very far from each other. For example, in this point and this point, they may look close to each other, but to get from here to here, you have to traverse the whole manifold. Okay, so it's important for us to separate them. So let's see how the autoencoder can handle that. Okay, so that's the data set, and I'm gonna build the nonlinear autoencoder. Okay, so let's have the 3-layer hidden dimension that has 128, 64, and 32 dimension. And then with that, we can build the encoder. So first, I want to specify the encoder layers, and the previous dimension is input dimension. And now we can knit the layers together. So for hidden dimensions, we extend the encoder layers. Okay, so then we have this, we extend each linear with a ReLU. We can add let's just be fancy. Let's add a batch norm, which requires hidden dimension, of course. Okay, so we still need to add one more, right? Because we want to go to the latent, so yes. So for the decoder, we just need to mirror the architecture, right? Just mirror the architecture that we built. Okay, let's see how we can do it. So decoder layers and prev dim is latent dim. We start from latent dim. And then for hidden dimension, now we have to reverse, right? So that's that. Extend, start from prev hidden, relu, batch norm, and then prev is hidden. Yes, good. And what's the reconstruction? So for the final reconstruction, we have to append, of course, the n linear. That will be our decoder. So we still have to define the input and latent, which is this that we defined at the beginning. Okay, latent. Good. So that's the construction. Now we can easily call encode takes in X and return Z self encoder. The decode will be similarly self, but now it takes in C. We just need to do a forward. So reconstruction will be the decoded latent. And then we can return the reconstruction just like before and Z. That's our nonlinear autoencoder. Now let's do the experiment. So we will generate a Swiss roll. We will sample like 2000 times from the Swiss roll. We have to inject some noise, and the resultant will be a three-dimensional point cloud. Of course, we have to normalize the data for a stable training in this case. Because of the complexity of the data, we are looking at the spiral that is living in a 3D. We are expecting a 2-dimensional manifold to be found, which is just a plane that is just spiraled. We will compare this nonlinear autoencoder with PCA and the linear autoencoder that we wrote earlier. Okay, so I'm going to code this up because this is easy. I will show you the final result. So here is what I did. I have the samples taken from the Swiss roll, normalization, some print statement. We do the PCA and then the linear autoencoder. Of course, we have to train that. And then the nonlinear autoencoder. Here, I reduce the dimension to somehow be fair, really, because it's not really necessary to go that deep too. Okay, so we can visualize the Swiss roll, both in 2D and 3D. And the most important experiment is the reconstruction. We can also look at the training curves. Okay, so with that, here is the result. So you see the reconstruction error. Of course, for PCA and linear autoencoder is the same because they are the same. But here is the reconstruction error for the nonlinear autoencoder, which is extremely small compared to the other two. And here is the result, looking at 2D and then the 3D reconstruction. So you see that the PCA reconstruction is basically just giving us a much simplified reconstruction. That's why it's very poor in the reconstruction error, as you see here. And for the nonlinear autoencoder, you see the training is going down smoothly. That's how we show that the nonlinear autoencoder can handle much more complicated data sets and then finds better representation of that.